Let's jump right in. Welcome to this explainer. Today, we are going to break down exactly how computers take our messy, incredibly complex real world and actually understand it using the absolute elegance of linear algebra. Seriously, if you've ever wondered how a machine learning algorithm takes physical reality and turns it into pure data it can learn from, you are in exactly the right place. So how do computers actually read the real world? Well, before any AI can do its magic, it hits a wall. It absolutely has to translate real-world objects and behaviors into a numerical language. It doesn't see a person, a house, or a stock market. It literally just sees numbers. And how we structure those numbers, that is going to make all the difference in the world. Here is our roadmap for today's explainer. First, we'll look at translating data into math. Then we'll dive into vectors as single data points, scale up to matrices as tables of data, figure out how to manipulate that data, and finally, bring it all together with systems of linear equations. Let's get to it. All right, part one, translating data into math. This is all about bridging reality and computation. In machine learning, we usually organize our data into tabular formats. Think of it like a giant spreadsheet. Each row is a specific example, maybe an individual person, and the columns represent numeric features about them. You'll notice we completely ditch names or personal identifiers. An algorithm doesn't care what your name is, right? Plus, dropping it protects privacy. We only care about the hard, quantifiable features, things like age, income, or specific categories, all mapped out perfectly across these columns. Moving right along to part two, vectors, which are our single data points. These are the fundamental units of our data. Okay, so if we pull just one single row from that giant table, we get a vector. Formally speaking, a vector is just an element of Rn. That's really just a fancy mathematical way of saying it's an ordered array of real numbers. For us, this single vector perfectly captures every recorded feature of one specific individual. It's the core building block we feed directly into the machine. What's fascinating here is how the exact same concept looks totally different depending on who you ask. To a computer scientist, a vector is just an array of numbers. It's a list taking up space in memory. But ask a physicist, they see that exact same vector as an arrow shooting through physical space, complete with direction and magnitude. And in machine learning, we actually need both. We use the computer science view to physically store the data, but we rely entirely on the physics view to measure the geometry and relationships between all those different data points. Which brings us to part three, matrices, our tables of data. Here's where we scale up to the full data set. When we take a whole bunch of these individual vectors, or rows, and stack them up, we get a matrix. Basically, it's a rectangular grid made of m rows and n columns. This is a massive deal, because a matrix lets us take our entire data set, the whole massive spreadsheet, and shrink it down into a single, highly manipulatable mathematical object. This perfectly illustrates exactly why matrices are so crucial. They allow us to compactly write out incredibly messy, multivariable real-world problems. Let's say you're trying to calculate an optimal factory production plan. You've got multiple products, all needing totally different amounts of various resources. Instead of writing out hundreds of separate equations to track every single nut and bolt, we just capture the entire resource allocation problem right inside the clean, efficient structure of a matrix. Game changer, right? Now for part four, manipulating the data. Let's look at the rules of the road for matrices. So to actually solve problems, we need a few specific mathematical rules to manipulate these matrices. Addition is super straightforward. You would literally just add the matrices together element by element, assuming they're the exact same size. Scalar multiplication is also a breeze. You just take every single number in the matrix and multiply it by one specific value, which basically scales your whole data set up or down. But the third rule, matrix multiplication, that's where things get really fun. The big takeaway here is that when you multiply two matrices together, you don't just multiply the matching elements. It's not that simple. Instead, you compute what's called the dot product. You literally take an entire row from the first matrix, match its elements to an entire column in the second matrix, multiply those pairs, and add them all together. And all of that math just gives you one single number in your new matrix. It's a highly intertwined operation. Because of this intricate row-by-column dance, you've got to be super careful. Sure, some standard math rules apply, like associativity and distributivity, but matrix multiplication is generally not commutative. That means A times B is almost never going to be the same as B times A. The order you arrange your datasets completely changes the end result. In fact, if the inner dimensions don't match up exactly, the multiplication is literally impossible to do. All right, the final stretch. Part 5, Systems of Linear Equations. Time to put all these blocks in motion. Now we take our matrices and our shiny new rules and we apply them to actually solve problems. Any system of linear equations can be written in this incredibly elegant form, AX equals B. Here, A is our matrix of known coefficients, basically the fixed rules of our system. X is the vector of unknown variables we're desperately trying to find, and B is the vector of known outcomes. Setting it up this way neatly separates our hard data from the unknowns we're trying to predict. Once we've got our system set up, we smash the A and the B together into what's called an augmented matrix. From there, we just systematically apply our manipulation rules. We swap rows, add them, scale them, step by step, aiming for a clean layout called row echelon form. It's a systematic way to peel back the layers and isolate our unknown variables until the final solution is just sitting right there, staring at us. To really lock this in, let's step away from the numbers for a second. We can translate all this abstract algebra directly into visual geometry. As the foundational rule brilliantly states, since a solution to a system of linear equations must satisfy all equations simultaneously, the solution set is the intersection of these lines. This geometric interpretation is the ultimate visual payoff. Every single line represents one linear equation from our matrix. So solving the matrix equation isn't just mindlessly pushing numbers around on a page, it's actually finding that exact point in space where our different data relationships perfectly align and intersect. You're literally finding the point where everything agrees. And because these equations represent straight lines or flat planes if we're in higher dimensions, the geometry tells us a pretty profound truth. There are only 3 possible outcomes. 1, the lines intersect perfectly at exactly one point, so we have one unique solution. 2, the lines are totally parallel and will literally never touch, meaning there is absolutely no solution. Or 3, the equations actually represent the exact same line stacked on top of itself, meaning we have infinitely many solutions. The geometry completely dictates the limits of our data. Which leaves us with a truly mind-bending challenge. We just beautifully mapped out 2 features as 2 simple intersecting lines on a flat plane. Super easy to see, right? But out in the real world of modern data science, an image or genetic sequence might have millions of features, meaning millions of dimensions. If human brains can't even visualize a space with a million intersecting planes, how on earth do we build algorithms to compress and manipulate those massive matrices to find the hidden intersections? Well, that's exactly what linear algebra allows the computer to do. Thanks so much for joining me for this explainer today, and I'll catch you next time.